Let's look at the back side of our 7.3 notes. We want to write down a couple of those properties that we just talked about. And if it was me, I would put them up here in this little corner. Okay? That gets them up out of the way. You can highlight them, you can circle them, you can do whatever you do, but you can write them wherever you would like. There are 3 properties that I want you to write down. First one came from one of our homework assignments, or at least we noticed it in one of the problems there. And that one simply says, and we're going to call these, by the way, we're going to call these the properties of logs. Okay, properties of logarithms. So the first one I want then is log base b of a negative number. So base b just means any base, right? Any logarithm of any base of a negative number, that is going to be undefined. Okay, that's going to be undefined. The next one, we saw this yesterday. I believe we also saw one of these in the homework. But if we have log base b of 1. Log base b of 1. Now remember, the way that logs work, what we're really asking ourselves is b raised to what power equals 1? 0. That's exactly it. So therefore, log base b of 1 is going to equal 0. The log of anything, log base anything of 1 always equals 0. Okay? We have another property here. This is one that's on the front side of your notes, but it's just kind of written small. You could overlook it, so we're going to write it here. If we have log base b of b to the a power, that will equal a. That one we saw in our homework as well. Log base b of b to the a power equals a. And then the other one, which hasn't shown up yet, but we will see it in the future, so we want to make sure we have it here written down. Again, it's on the front side of our notes. But if you have b raised to the log base b of a power. Okay, so that whole thing, log base b of a, that's the exponent on b. Okay? So if you have that, that will also simply equal a. So there we go. We have 4 properties of logarithms that will show up from time to time here in the next couple weeks. So make sure you have them in your notes. Make sure you write them down somewhere. Highlight them. Do whatever you need to do so that you know where they're at. Okay? All right. There is something else that I want you to add to this. Something else I want you to add to this. It's called the common log. Okay? It's the common log. And the common log is log base 10. I'm just going to say log base 10 of x. Okay? So log base 10 of x. It's called the common log. Well, a couple of reasons. One reason is because it is easy to use. Okay? It's easy to calculate. 10 raised to powers are easy to calculate. Okay? And so when back in the day, they didn't have calculators to help them do stuff. Okay? We sent people to the moon without calculators. All right? And they did that because they actually used to be able to buy books that had nothing but tables in it. Math tables. Okay, so that's where you'd find your sine, cosine, tangent, and all that kind of stuff just on a bunch of tables. You would find logarithmic tables, okay, in there so that you could find out what is the log base 10 of 57. Okay, and you could look that up on the table and it would tell you in a 4-digit approximation of what that would be. Okay, I have one of those books at home. I'll have to see if I can remember to bring it in and show you guys. It's kind of neat just to see what people used to use. That was their calculator, that in their brain. Okay, but point being is that base 10 is easy to calculate, and so it was easy to make those tables. Okay? Another thing that why 10 is the common log is because we have 10 fingers, 10 toes. Our entire number system is based off of 10. It's the decimal system, DEC, like a decade is 10 years. A decagon has 10 sides. The decimal system has 10 numbers involved. Okay? So our entire number system is based off of 10. Okay, and so therefore, it's the common log base 10 of x. And since we use it so often, mathematicians are kind of lazy people. We don't like to write things that can just be assumed. And so therefore, rather than writing log base 10 all the time, they just write log. So if you ever see log x, or log of some number, log 5, it means log base 10 of 5. Okay, it's the common log, and so they stop writing the 10. The 10 is assumed. Unless it's written as something different, it's assumed to be a 10. Okay? So now that you know what the common log is, you then know what that log button on your calculator does. That log button on your calculator only calculates log base 10. Because all it says is log, right? Well, that's the common log, so it only calculates log base 10. And you can prove that to yourself by putting in there what is log of 100. Well, think to yourself, what is 10? What power, 10 raised to what power equals 100? 2. So therefore, log of 100 should equal 2. Because log base 10 of 100 is 2. Okay? So, there you go. Common log. Now, we want to go through and talk about the graphs of logarithmic functions. And to talk about the graphs of these, we need to remind ourselves of exponential functions. So, in red here, I have an exponential function y equals 10 to the x power. So we have 10 to the x is our exponential function. The inverse of that is then going to be log x. Why just log? What's the base? 10. It's log base 10 of x. So a couple things to remind ourselves of. As I plug in numbers into my exponential function, if I plug in 0 for x, 10 to the 0 power is 1, so that's where I get the point 0, 1. 10 to the first power is 10, so that's where I get the point 1, 10. And then I have my function. Also, exponential functions have their asymptote at the x-axis, right? Okay. Well, we said yesterday, and I'm saying it again here, that logarithms are the inverses of exponential functions. And so inverses, back when we did those, we said that they were always reflections of each other along the line y equals x. You guys remember doing that? We'd graph a parabola, and then we'd reflect it, and it would give us a parabola on its side. Same thing here. Right here is our line of reflection, x equals y. And so if I was able to actually fold this graph, you would see that that red graph would fold over to become that blue graph. All right? And there's other things that happen here as well. Because remember, back when we were graphing inverses, we said, well, all we need to do is flip the x and the y, right? And that worked for our t-charts as well. If you flip the x and y coordinates, you get the inverse. Same thing here. 0, 1 becomes 1, 0. 1, 10 becomes 10, 1. And there's the graph. Same thing goes for the asymptotes. The asymptote for an exponential function is at the x-axis. So looking here, this little part here, going from the negative side of the x-axis to the origin, if I were to fold that over my reflecting line, it would reflect down here, right? But when I fold that over, same thing goes for the positive side of my x-axis. If I were to fold that over, fold that across this reflection line, I would get the positive y-axis. So what it's telling us by looking at this is that if the x-axis is our asymptote for an exponential function, then the y-axis is the asymptote for a logarithmic function. Okay? We need to keep that straight because on your test coming up in a couple weeks, you're going to have both exponential functions and logarithmic functions to graph. So you got to remember which one's which. Exponential functions have an asymptote at the x-axis. Okay, they sound the same, so therefore they go together. Okay? Logarithmic functions Their asymptote is at the y-axis. Okay, so let's keep looking here. I said that they're inverses of each other. How did we get that they're inverses? Well, let's start out with our function y equals 10 to the x. When we did inverses, we said we flipped the x and the y. So let me go ahead and flip the x and the y. Okay, so there's the inverse. The issue here is that we don't want our output to be up here as an exponent, right? Remember, y is always the output of a function, x is the input of the function. Okay, so we don't want the output up there, so we want to write it as y equals. The whole point is that we want our equation to say y equals, our output equals what? And this is why people came up with that logarithmic notation. This is where that logarithmic notation came from, and so that we can say y equals. And so in this case, the base of our exponent is 10, and so the base of our log will be 10. I'm not writing it because that's the common log, right? So therefore, y equals log x. It is the inverse of that guy. Okay? So, logarithmic functions, they're inverses of exponential functions. That tells us then where the asymptote goes. And now is going to be the reflection of the x-axis, which is the y-axis. So, looking at an example, just take a look at this first example here. We want to know what is the graph of y equals log base 3 of x. So y equals log base 3 of x. First things first, in order to graph that, I want to go ahead and rewrite it in exponential form. I do not graph from log notation. Okay? Because really people don't think in terms of logs. People think in terms of exponents. If you have to think at all, you're going to be thinking in terms of exponents. You're not going to be thinking in terms of logs. So we want to change our equation to exponential form. So you might want to go through and rewrite that so that the log comes first, seeing as how that's how we got used to seeing it yesterday, right? We got used to seeing it that way yesterday. And so now, how would I write that log as an exponent? Remember that recycle visual? 3 to the y power equals x. 3 to the y power equals x. It means the same thing. Log base 3 of x equals y is the exact same thing as 3 to the y power equals x. It's just a different way of writing it. Okay? So now that we have that, we can actually plot points. We're going to make a t-chart. And here's the thing. In the past, we have been plugging points in for x, right? We've been plugging points in for x, solving for y, because of course that makes sense. X is our input. So input a number to the equation, we get our y as our output, so we'd get a number out. The problem with this is that what we're solving for is in the exponent. That makes it real hard to do, right? So since we're the ones taking control here, we're the ones plugging numbers in, don't plug in for the x. When you're solving or graphing logarithmic functions, plug your numbers in for y. Plug your numbers in for y. It makes your life easier. Why would I want to do that? Well, because y is the exponent. Makes my life easy. And so now if I plug y into my equation, I get 3 to the negative 2 power, which is what? 1/9. If I plug in negative 1, 3 to the negative 1 power is? 3 to the 0 power. 3 to the first. And 3 squared. Okay? So that gives me a t-chart that I can now work with. So that t-chart I want to graph. So if I graph 1/9 negative 2, 1/9 is super small. With the thickness of my pencil lead, I'm not going to be able to graph that where it's really supposed to go. So I'm not going to graph that one. It's on my t-chart. You need it on your t-chart, but I'm not going to graph it. But I can approximate where 1/3 is going to be. So 1/3 on the x, -1 on the y is going to be somewhere around there. Please make sure that you're plotting these in the appropriate location. Pay attention to what your x coordinate is and what your y coordinate is. Then I have 1, 0. I have 3, 1. And I have 9, 2. Oops, 9, 2 right there. Please remember, logarithmic functions have an asymptote at the y-axis. The y-axis. So when I graph this, my graph will look something like this. Okay. So describe the domain and the range. So domain was which parts of the graph?
How far it traveled to the right and left.
Oh, so x.
Yeah.
X is the domain. Very good. So what is the domain of this?
From 0 to...
Ooh, can x be 0?
No.
No, x cannot equal 0.
Negative infinity?
Nope, we can't go to negative infinity either because our graph does not go in that negative direction over here.
Oh, wait, I thought you...
1/3.
It would go from...
1/3.
Nope.
No, how far is it?
X coordinates. What are the x coordinates that we can have?
From 1 to...
From 0 to infinity. Can it equal 0? No, it can't equal 0, but it can be 0.0001.
Oh, I wasn't done.
It can be a number just a little bit bigger than 0, right? Okay. So, the x domain are all numbers, basically all numbers greater than 0. Can be our x-axis. Which, by the way, is why you can't take the logarithm. You can't take the logarithm of a negative number. Because those don't exist on the graph. Okay? We can't take the log of a negative number because those negative numbers aren't on the graph. You can't take the log of a negative number because they're not there. They're undefined. Okay? What about the range? Range stands for our y-axis, y values. What can those be?
Negative infinity to positive 2.
Negative infinity to
Or positive infinity.
positive infinity. You can definitely see that the y coordinates are going to go down forever, but they're also going to go up forever. As we go this way on the graph, it's going to get there slowly, but eventually it will get to positive infinity. Okay? So there is a restriction on the x. We can only plug in numbers greater than 0, but the y has no restriction. Our output can be all real numbers. Very good. Let's see. How about the y-intercept? What would that be?
No, it'd be...
It doesn't have one. There is no y-intercept. Because on this graph, the y-axis is the asymptote, which means our function approaches that line, but will never ever get to the line. It gets closer and closer and closer and closer to infinity, but never gets there. So there is no y-intercept. Okay, and then the asymptote, I just said, was the y-axis. The y-axis is the asymptote. Okay? So, some kind of new ways of thinking about our logarithmic functions. Let's try one more. Looking at our next example here. This one, we have shift. The nice thing is about the shift, it's the same as it's always been. It's the same as it's always been. One thing you've got to be careful about with logarithmic functions, though. Okay, here's just an example. If I have y equals log, I'm going to do the common log base 10, log of x minus 3. That is giving me a vertical shift down 3. If I have y equals log of x minus 3, that's a different story. Now I have a shift to the right 3. So you have to pay attention. In logarithms, if it's attached to the x, making it our left and right shift, it's got to be in parentheses with the x. They're saying that they want the log base 10 of that entire thing. Log base 10 of this entire thing. Whereas up here, it's just log of x. Okay? So if there's no parentheses, then it's just the log of that first number. There has to be parentheses if they want you to take the log of the entire quantity. Okay? With me? All right. So in our example here, it's actually easy to see because we have both shifts. All right? We have the shift that's with the x, and we have the shift outside. So we are going to shift where in our problem here? We're going to shift to the right 3. We're going to shift up 4. Right 3, up 4. Just like we've done all year long with all of our graphing problems, we now ignore the shift. Okay? We've always done that. Find out what the shift is, now ignore it. And if I wanted to, I could flip that around so that I have it written the same as I did yesterday. Log base 4 of x equals y. How do I rewrite that in exponential form? Say that again? That's exactly it. 4 to the y power equals x. 4 to the y power equals x. And I now go through and make a t-chart. And look, the y is in the exponent. The y is in the exponent. So therefore, it's going to be easier for me to plug in for y than it would be to plug in for x. So that's what I'm going to do. Plug in for y. And if I plug in negative 2 for y, what is 4 to the negative 2 power? How about 1/16? What is 4 to the negative first power? 1/4. What's 4 to the 0? 4 to the first. 4 squared. All right, some of these points I can graph, some of these I cannot. So let's go ahead and mark the ones I can graph here. I can't graph 1/16, but I can graph 1/4. So 1/4 on the x, negative 1 on the y brings me somewhere right around in there. 1, 0 be right there. 4, 1 would be there, and 16, 2 I can't graph. Okay? So we are shifting. Now, if I shifted this graph up and down, is that going to change my asymptote, since my asymptote is now the y-axis? No. But a shift left and right does. A shift left and right does. We are shifting to the right 3, so our asymptote moves to the right 3. Okay, so there's the new asymptote, and each one of those points that we plotted, the 3 points we plotted, gets shifted right 3 up 4. So going right 3 up 4 brings me right about here. Right 3 up 4. And right 3 up 4. So our graph of this logarithmic function will look something like this.